just as, by the way, Gunter, is it an hour? Is that the?
Yeah, between an hour and 1 hour and a half, something like that.
Oh, okay.
Yeah.
Okay, so we'll see how it goes. So I'll remind you of a few things first. So first of all, prickly forcing. So suppose that U is a normal measure over a cardinal nu. So the prickly poset consists of there was some message flashed from the host on the screen. It consists of pairs SA, where S is a finite stem from nu and A is a measure one set. And I'll take the maximum of S to be less than the minimum of A. And extension is given by TB extends SA, if and only if T extends S. The difference coming from A, and you shrink the measure one set. So this is well known. If you take G, which is V generic over this poset, then it changes the cofinality of nu to be omega. And it preserves cardinals less than or equal to nu because it adds no bounded subsets of nu, and it preserves cardinals greater than or equal to nu plus because it's nu plus CC. And so we end up changing the cofinality of nu to omega without changing cardinals. Okay, so that motivates some of the results. I'll get to why. And I want to also remind you of the Mitchell order. So this will be just on normal measures. There are ways of talking about the Mitchell order on more general objects as well. But for normal measures, U0 and U1 over nu, U1 is Mitchell below U0 if U1 is in the ultra power by U0. And this is a well-founded relation. I won't prove it. And the rank of this relation restricted to normal measures over nu is written O of nu. And well, you get a better bound than just by counting the number of ultrafilters. In fact, Mitchell showed that O of nu is less than or equal to 2 to the nu plus. So if you have GCH, then of course nu, the bound is nu plus plus. And the order can be very complicated, but in K, which is the main model I want to talk about, and other inner models that have that could have measurable cardinals, the Mitchell order is linear. Let's see, do I want to? I think I will stop to draw a picture. Maybe later I'll draw a picture if there's time. Let's see. Okay, so there's a companion to prickly forcing, or an extension of prickly forcing due to Magidor, 1978. And it's for changing cofinalities to be uncountable. So take a kappa, which is regular, uncountable, and less than nu. Assume that nu is a measurable cardinal, and also assume that the Mitchell order of nu is at least kappa. Then there's a poset, which I won't write down, P, such that if G is a V generic filter over P, then in this generic extension, you change the cofinality of nu to be exactly this kappa. And you don't change cardinals. It preserves cardinals. It does add bounded subsets of kappa, but there are other reasons why it preserves cardinals less than or equal to kappa, less or equal to nu. Okay, so those motivate well, those came out long ago, and they motivated a lot of work. So I'm actually going to jump to the theorem that I want to talk about and then back up and tell you stuff that came in between this theorem and those forcing results that I just listed. So the theorem that I want to talk about is the following. So assume there's no transitive class model of ZFC with a wooden cardinal. Okay, one thing you need to know already at this point is that K exists. So the core K is the core model, and work of first Steele and then Steele and Jensen tells us that under this first assumption, what's known as K or true K exists. And it's one of these inner models that I've mentioned already. I'll describe it a little bit more eventually. So now suppose that nu is a singular ordinal such that nu is bigger than omega 2, and the cofinality of nu is less than the cardinality of nu. Okay, so that's all in V, but suppose that K is dramatically incorrect and thinks that nu is a regular cardinal. And the conclusion is, the first conclusion is that, well, then nu is actually a measurable cardinal in K. And then we can also say something about the Mitchell order. If the cofinality of nu is bigger than omega, then the Mitchell order of nu in K is bigger than or equal to whatever the cofinality of nu is in V. Okay, and then there's a technical caveat that I'll mention now and then I'll mention again later. There are two flavors of inner model or extender model in vogue, and maybe there's some that are less in vogue, but those are the two main ones in vogue. And the style that is assumed for the results above is that K is constructed using Jensen indexing. If you make an additional GCH-like assumption that 2 to the cofinality plus is less than the cardinality of nu, then the results also hold for K constructed using Mitchell-Steele indexing, which is the other popular style that, that you might use for building K. I guess I might say this again later, but I want to say that this this provides companion results for both the Prickry and Mogidor results. And it explains why in the Prickry case you need a measurable cardinal in order to change the cofinality of a regular cardinal to be omega by forcing, and then more generally in the Mogidor case to change it to whatever it is. It matches the large cardinal assumption in each case. And this theorem shows that, but actually that was known. And so now I'm going to tell you a little bit about the history. So first I'll tell you about the immediate precursors to this theorem, and then I'll go farther back in the history and list everything up to this theorem again. So let me just take a sip. Okay, so the immediate precursor to the theorem that I just listed, that I just stated, is this I'm giving the publication date, 1995 result with me and Bill Mitchell. And actually, the theorem that I already stated implies this theorem, but and this theorem is used in the proof, and also the methods are used in the proof. So anyway, this is the new theorem is really just a direct extension of the previous theorem. So let me read that to you. So again, assume there's no transitive class model of ZFC with a wooden cardinal. Then K exists. Let nu be a successor cardinal of K greater than omega 2, then the cofinality of nu is greater than or equal to the cardinality of nu, right? So you can derive this from the previous theorem just by noting that successor cardinals are not, provably not measurable. And so if you just use propositional logic, you realize this follows from the more recent result. I guess I should mention that the fact that K exists based on this assumption was not known in 1995. So at the time, it was the Steele core model, which had some kind of ZFC plus epsilon plus no inner model of a wooden cardinal assumption as the background. So anyway, that was eliminated at some point in between then and now. And the most popular corollary to this result is that if K exists, then it correctly computes successors of singular cardinals. Okay. So as I said in the abstract, this is just repeating the abstract, I want to say something intuitive and wildly incomplete, but not entirely misleading about what the theorem means, how it is proved, and what came before it. Before I continue, is there something I should add? Give me some nudge me in the right direction if I'm going, if I'm straying. Anyone? Okay. All right. So right. So here's here's a list of earlier results that on which the current theorem builds. And these are not chronological. They're in order of the large cardinal hierarchy. And you'll notice they really aren't in chronological order. So the earliest and first result that got the whole area started, I would say, is Jensen's covering lemma for L. And so Jensen, you can view Jensen's covering lemma for L as proving the same theorem that I stated, assuming that zero sharp doesn't exist. And you also note that there are no large cardinals in L, and so that possibility is excluded. Then the next result, which is a companion to the Prickry result, it explains why Prickry forcing needs a measurable cardinal, is the Dodd-Jensen covering lemma, which, okay, so I said, so one way of building the Dodd-Jensen core model is assuming there's no inner model of measurable cardinal. That's too restrictive an anti-large cardinal hypothesis if you want to get inner, well, I guess you can get an inner model with a measurable cardinal. A better way of thinking about it is, with analogy, at this level, what's analogous to zero sharp would be zero dagger. So you can build it assuming zero dagger doesn't exist. in any case, you get an inner model with a measurable, if there's a failure of covering of the kind that I was talking about. And then motivated by, directly motivated by the Mogador result, which was earlier, Mitchell extended the Dodd-Jensen result to K under the assumption that there's no inner model of ZFC with a measurable of maximal Mitchell order. He gets exactly the result that that the two of us proved more recently, and I stated under that more restrictive hypothesis. Then, well, a lot of stuff happened in next. In the early 90s, Steele came up with the core model below a wooden cardinal, and but then the theorem that I stated was proved under a more restrictive anti-large cardinal hypothesis. Either you can view it as there's no inner model with a strong cardinal, or more generous, there's that zero pistol does not exist. So zero pistol corresponds to indiscernibles for the minimal inner model with a strong cardinal. So Sean Cox proved this theorem under the more restrictive hypothesis, and the techniques we use owe a debt to Cox's paper as well. So it kind of combines his paper with the earlier paper with Mitchell. Then in a paper published in '97, which actually predates the '95 paper, is this triple paper in which we get the correct, the K compute successors of singular cardinals correctly, and the more general version of that, but under a kind of the assumption that that the cardinality of nu is countably closed. So there's an extra assumption about cardinal arithmetic in that result, and then I already mentioned this. Okay, so what's the plan? I'm going to prove the theorem for L, or at least outline the proof of the theorem for L. Of course, L doesn't have measurable cardinals, so that rules things out, rules some things out. So I'm going to be assuming zero sharp doesn't exist and show you what happens. By the way, K is L if zero sharp doesn't exist. And I'll mention some details of that proof that come up in the proof of the current theorem. So it's so in particular, I'll mention what sort of elementary substructures of something are relevant to making the proof work, and the same kinds of substructures will do more for us when the situation becomes more complicated. Then I'll move on to the Dodd-Jensen K, assuming that zero dagger doesn't exist, but I'll explain what that model looks like from the modern perspective. So that model is also K if zero dagger doesn't exist. Anyway, so I'll do that, and then at the very end, I'll tell you sort of what you need to do beyond, to get beyond zero dagger. And the style of proof will be, or the style of outline, many times I'll end up saying, well, further analysis shows the following, and I'll give no reasons how that analysis goes, just because something needs to be omitted. So let me just see, how am I doing? All right, so let's take a look at L. So assume nu is a singular ordinal bigger than omega 2, and the cofinality of nu is less than the cardinality of nu, but nu is a regular cardinal in L. Let's see what happens. So let's let capital omega be a much larger regular cardinal. Okay, it doesn't have to be that much larger. I think cardinality of nu plus is enough. But anyway, it's up in the sky. And let's take an elementary substructure of H omega. Let's assume that the cardinality of X is smaller than the cardinality of nu, and that the sup of nu intersect X is nu. So it's witnessing that the cofinality of nu is small. And let's take the Mistovsky collapse, call that pi. Oh, why? Oh, I'm taking the inverse of the Mistovsky collapse. And let's let delta be the critical point, and let's let mu be the preimage of nu. And let's let omega bar be the ordinals of n, L bar be L of n. And then we know that delta is less than mu, and that's less than omega bar. And by condensation, L bar is actually just L omega bar. Okay, so there are two cases. So the first case, I'm just going to show that zero sharp exists. And the first case is that all constructible subsets of delta belong to L bar, which, by the way, would be the same as saying they belong to n, because n's version of L is just L bar. Okay, so then in this easier case, we'll derive an ultrafilter over L with critical point delta. So U pi will be the set of A contained in delta, such that A belongs to L, and delta, so A belongs to L, but then it can be moved by pi. And if we pick up delta in pi of A, then we put A into U pi. So this is an ultrafilter over L. So it's an L ultrafilter. We can take an ultrapower. If it's well-founded, then we identify this ultrapower with the Mistovsky collapse and obtain an elementary embedding pi tilde from L to L with critical point delta, and so zero sharp exists. Which I guess if we were going for a contradiction, that would be a contradiction. Okay, so I said if it's well-founded, is it? So one condition that would imply well-foundedness for this one, in this particular easier case, is if X is closed under omega sequences. But in order to arrange that, we would need that the cofinality of nu raised to the omega is smaller than the cardinality of nu, and that may or may not be true. And we don't want to add an assumption to the theorem. So there's an alternative condition. There's a stationary set of X's that work. I'm going to describe what the stationary set looks like with the bias towards the more complicated theorem below wooden cardinal. You might be able to get away with less if you're just interested in L. But let epsilon be the maximum of omega 1 and the cofinality of nu plus. Then epsilon is less than nu by the assumptions we made about nu. Build an internally approachable chain of length epsilon. So internally approachable means you add initial segments of the chain at the next stage. These are elementary in H omega. We want to throw in nu and keep the models smaller than epsilon. Then there's a club in, that is not, that's not omega. You know what? Sorry, I think I corrected this typo. And sorry, I just want to check something. That's the right file. Okay, I corrected this typo, so I'm worried that I somehow am using the file with other typos, but let's just live with it. Okay, so there's a club in epsilon, so that for every point of uncountable cofinality in the club, I, the corresponding xi gives you the well-foundedness we needed. All right, so this seems like a complicated way of saying something, but that's how you end. That's how the proof that there is such an X is organized. In any case, there's a stationary set of X to choose from. And for future, so I don't need anything about this, moreover, now, but I guess just as foreshadowing, when I get to the, well, even to the Dodd-Jensen core model, and then later to the more recent result, the same kind of X's will give us well-foundedness and iterability, except that in the current theorem, we'll have to do some shrinking. We'll have to do some pressing down and get an even smaller stationary set. And I'll mention where that's used when we get to it. Okay, that's probably too much information at this moment. So let's go on and talk about the harder case for L. The alternative to the easier case is that not every constructible subset of delta belongs to L bar. Hence, not every constructible bounded subset of mu belongs to L bar. So there's a unique beta where you add such a constructible subset, a bounded subset of mu that doesn't belong to L bar. And so we have delta less than mu less than omega bar. And then later on, where this point where you add a new bounded subset of mu, beta, then less than beta plus 1. All of this stuff is less than nu because nu is a much larger cardinal in L. And L beta and L bar have the same bounded subsets of mu, while L beta plus 1 has an additional bounded subset of mu. And I'm going to put P equal to L beta. Okay, here's a minor fib. Among many minor and major fibs, so L beta should really be J beta, where J is the Jensen hierarchy. And yeah, so let's just let that slide. So Jensen fine structure tells us that for some mu bar less than mu, for some n less than omega, and some parameter x in this P, P is equal to the Hall in P, the sigma n plus 1 Hall in P of mu bar union this singleton x. And yes, x could be the standard parameter, but I don't really need that for the argument. This mu bar is going to be the ordinal less than mu that P, but that such that definability over P adds a subset of mu bar. So So this property that P is the hull, this some mu bar, some x, singleton x, whatever, that's called soundness, and in particular sigma n+1 soundness for P, and I might refer to P as a mouse at some point. Okay, so continuing, we want to lift up P to get some R. And we're going to take an ultra power, which I'll call alt n p pi nu. It's the sigma n ultra power of P by the extender of length nu derived from pi. And I don't think I have time to say what that means, but I'm going to, at this point, you know, pi is an embedding from L bar to L sub omega, and you can derive an extender of length nu from such an embedding, and then you can form this ultra power by taking the ultra powers by the individual filters that make up the extender, and then taking a direct limit. So if you're familiar with that construction, then it's the one I'm using here, except that it's using sigma n definable functions over P. Okay, and then the same conditions on X that I dwelled on before imply that this alt n, that this guy is well-founded. And so I'll take its Mostovsky collapse and call that R. Okay, and then now I'm going to go faster and just say what some analysis shows. I'll do a little bit of it, but some analysis shows that, well, R is a level of L. The map pi tilde from P to R is actually sigma n+1 elementary. It agrees with pi up to mu +1. Okay, and now we get a contradiction. So the harder case doesn't even happen. X intersect nu is equal to the range, so the image of mu under pi, which is the same as the image of mu under pi tilde, which is contained in the image of P under pi tilde, but P is this hull. And so, and pi tilde is sufficiently elementary that when you move things over to R, R is the corresponding hull of the image of mu bar and some parameter, but the image of mu bar is contained in the value of pi at mu bar. So let's call this final set Y. Then Y is visibly definable over R, and so it belongs to L in a way that tells you it belongs to L. And then also visibly, the cardinality of Y isn't any bigger than the set you're taking the hull of. And so the set you're taking the hull of is this set together with one more parameter. But that's less than pi mu, which is equal to nu. And Y covers X intersect nu, but it's small. And so in L, this Y belongs to L, it's small, but unbounded in nu. And so the existence of this Y in L tells you that nu is singular in L, but that contradicts that nu is regular in L. Okay, so just summary. We just going back, we took a specially chosen elementary substructure. We looked at the Mostovsky collapse. If if all constructible subsets of the critical point were in the collapse, then we showed zero sharp exists. Otherwise, we just got a contradiction. And then when we well, let me just keep going. Okay, so we've done this. Okay, so now I'll describe the Dodd-Jensen core model a little bit, leaving out a lot. So assume zero dagger does not exist. And well, Dodd and Jensen proved K exists. But I want to think of K in the modern way, which is as an extender model. And so what does that mean? Well, K has the form L of E, where E is a sequence of extenders indexed by ordinals. So each of the extenders is either trivial, which I'm going to say is empty, or there exists some kappa. So when I say extender, what do I really mean? There's some kappa less than alpha, so that if you look at the structure, calling it M, where you take the universe of L of E constructed up to stage alpha, together with membership, together with the predicate that you used to build K up to alpha, together with this E alpha that we're adding at stage alpha, the thing we're adding looks like an extender with critical point kappa at that point. That's not to say that it really is. It just looks like one locally. And then because we're working below zero dagger, the extender is really just a measure reorganized. So the way to say that is that the only generator of U alpha is the critical point kappa itself. And so E alpha is just, it's essentially a normal measure over kappa over M. So it's M thinks, so this is the interpretation of a relation on the structure. And so with this extra predicate, we have what looks like a normal measure. Of course, when you go to bigger core models where zero dagger might exist, then you have to change that condition. Okay, and then what is the relationship between alpha, or so what's the condition that tells you when you're going to add stuff? Alpha has to be equal to the image of this critical point plus, and image under what? Under the ultra power embedding. So implicit here is that the ultra power is well-founded enough to make sense of this. So if you take the ultra power map coming from E alpha and then look at where the critical point gets sent, and then take the next cardinal in this ultra power and assume all of that stuff exists and is well-founded, that has to be alpha. So it's dictating at what point you put on extenders. This is known as the Jensen indexing. Okay, and the Mitchell-Steele indexing is different. It's earlier. The Jensen indexing is quite late. The Mitchell-Steele indexing is sort of as early as possible. Okay, and then there's something that's known as the coherence condition, which says that this ultra power is also an L of E model. And the extender sequence looks exactly the same up to alpha, but at alpha, you have nothing, right? So you started with M, which has something at alpha, and then you take an ultra power, you get a taller extender model. It has nothing at alpha. And that's used in comparing models. And then there's a fine structural condition. M is sound, more or less in the sense that I mentioned P is sound when I was talking about L. So if you add a new bounded set, then everything gets collapsed. And if you add a new sigma n bounded set, then everything gets collapsed in some canonical sigma n way. So that's what soundness means. That's a description of extender models. I've said nothing about what makes there are many extender models. Not all of them are K. And so I would have to say more about which one is K, but I'm not going to. I'll tell you where additional features are used later. Okay, so now I'm going to describe how you take the argument we gave for L and weaken the assumption that zero sharp doesn't exist and get a theorem. We get the Dodd-Jensen theorem for K under the assumption that zero dagger doesn't exist. Okay, so it starts off the same way. Assume nu is a singular ordinal bigger than omega 2. The cofinality of nu is less than the cardinality of nu. So there's a little redundancy, right? I'm saying it's singular twice, but I'm saying more here. But K is wrong about nu, and K in the sense that K thinks nu is a regular cardinal. Take some large regular cardinal omega, take some elementary substructure x of h omega of cardinality less than that of nu. Assume that x is unbounded in nu and that nu belongs to x. Mistovsky collapse, so everything is the same. Delta is the critical point. Mu is the preimage of nu under pi. Omega bar is the ordinals of the Mistovsky collapse n. But now K bar is what n thinks is K. Okay. All right. Then in terms of the ordinals, the way they're lined up, it's like before. There's no beta yet, but just delta is less than mu. Mu is less than omega bar is less than nu. And then K bar, without too much trouble, can be seen. You need to know the definitions, but it's an extender model. Well, it's an initial segment of it's a set extender model, which means it's L omega bar of E bar restricted to omega bar, where E bar is pi inverse of E cut off at omega. In some, okay, that's not literally true because E restricted to omega isn't a member of. it's the preimage of that under pi. It doesn't. Well, yeah. So it doesn't follow that. So even though K bar is an extender model, it doesn't follow that K bar is an initial segment of K. So that's a big difference between the situation here with K and K bar and the situation before with L and L bar. L bar was just a level of L, but K bar is not one of the, K bar is not just a level of K. And the reason why is because this E bar doesn't have to look anything, well, it has to look something, but E bar doesn't have to be an initial segment of E. The good news is, well, just without knowing anything about this, you can guess that it at least looks like E up to delta, but actually a little bit of argument, a little argument implies that, or a condensation lemma tells us that K bar agrees with K up to the next cardinal of k bar. So up to delta plus of k bar. And that's, well, another way of saying that is, I guess the way I'm saying it is, what that means is that E bar restricted to delta plus of k bar equals E restricted to delta plus of k bar. And that's useful information because these are models of GCH, and they're models of GCH in the same way that L is, which means that subsets of delta are all constructed before the next cardinal after delta in the models. And so this is giving us information about how the power set, this is telling us that the power set of delta in k bar is contained in the power set of delta in k. And yeah, there's no typo here, right? I'm not saying that they agree on what the next cardinal is. I'm just saying that the extender sequences agree up to that cardinal, up to that ordinal, which may or may not be a cardinal in K.
Can I ask a question before you leave that slide?
Yes.
When you take this elementary substructure of H omega,
Yes.
the extender sequence E is a predicate within that structure, and therefore it's also included in the elementarity of the.
Yes, and it's also definable over H omega.
Oh, okay.
Because K up to omega is definable in.
That's part of what was in parentheses down on the left corner, that you haven't actually said what E you're going to use.
Yes, exactly.
Really nice.
And if we wanted to, we could actually just take, we could go to, there are various options. We could use V omega plus 1 if we wanted to here, if we chose omega correctly. So, but yes, okay. So, so now, again, there's an easier case and there's a harder, and then there's a harder case. The easier case is the same. The K power set of delta should be the same as the K bar power set of delta. This statement that the two models K and K bar compute delta plus correctly is equivalent to these power sets being computed the same way. And that's because of the way GCH holds in K, or in any extender model. Okay, so this time we'll set U pi equal to the subsets of delta that the family of subsets of delta that belong to K, and when you apply pi to A, the subset, you pick up delta as a member. So you derive a K ultrafilter over delta from pi. And then we take the ultra power, call that pi tilde, and then we, as in the covering lemma for L, so we choose X either countably closed, if that's possible, or internally approachable in some way that's adequate to guarantee this ultra power is well-founded. And again, we identify the ultra power with its transitive collapse. We're not claiming that the transitive collapse of the we'll call it. I guess we were calling it R. In the proof for L, we were calling it R. We can call it R here too. So that's not I'm not claiming that is K. So the choice of X is used again to guarantee that this ultra power is iterable, and iterability here is Yeah, so I should say something about iterability, but I'll leave that out temporarily. The iterability of the ultra power is used with some further analysis to see that if alpha equals pi of delta plus in k, then E alpha is essentially U pi. So this tells us that delta is a measurable cardinal in K because U pi is coded by E alpha. E alpha belongs to K, and so U pi belongs to K, and so there's this measure over delta in K. Okay, but since zero dagger doesn't exist, that means that this is the only measurable cardinal in K. But because it's the only measurable cardinal in K, well, okay, it's the only measurable cardinal in K cut off at omega, so it's definable in H omega, so it belongs to the elementary substructure X, but delta is the critical point, so it's missing from the range of pi, which is X, right? So that's a contradiction. Okay, so there's another, you still get a contradiction in the easier case. Okay, so what does the harder case look like? So again, let's take a sip here. So in the harder case is not the easier case. We're still below zero dagger. So remember, if you assume zero dagger doesn't exist, then you can have a measurable cardinal in K. You just can't have any indiscernibles for it. So you can't get the next mouse. You can't get some kind of the next approximation to a second measurable cardinal. It just looks like L after you just construct after you get to the measurable cardinal. Okay, so now we're assuming K has bounded subsets of mu that don't belong to K bar. And we had I guess this is a warning, K bar is not necessarily an initial segment of K. So we need to show that nu is a measurable cardinal in K. We can't get a higher Mitchell order because we're assuming zero dagger doesn't exist. But we do want to show that nu is a measurable cardinal in K to complete the proof. And when we do that, we're going to end up seeing that K is constructed from the unique normal measure on nu in K. But this is the traditional way of describing L of U. We've described K as an extender model. Of course, it's the same universe, but the descriptions are different. Okay, and all of that can be fleshed out. Okay, so now so we're working towards seeing that nu is a measurable cardinal in K. So let's co-iterate K and K bar. So now I am going to describe iteration, in fact, co-iteration. So in the argument that I didn't give, I would have been co-iterating K and the ultra power of K by U pi. Here I'm co-iterating K and K bar. Let me describe what it means to co-iterate. So we'll have I and I bar. These will be iterations of extender models with models on the iteration M eta and M bar eta. That'll be my notation. And this will be for eta less than or equal to some theta, where theta plus 1 is the length of the co-iteration. M0 is K and M0 bar is K bar. Okay, so how do you define the iteration? So the successor steps, if you've defined M eta and M eta bar, you look at their extender sequences, and you look at so you look at them ordered by the the indices of the extender sequences are ordinals. You go to the least point of disagreement. So that means, well, one possibility is that you have E alpha and E alpha bar, but okay, so F, let's use, no, we have F for different reasons. M eta has its extender sequence, M eta bar has its extender sequence. And you go up those extender sequences to the point where either you have an extender on each side, but they're not the same, or you have nothing on one side and something on the other side. And then you apply whatever you have. And remember, the coherence condition says, well, if you apply an extender from the extender sequence, it disappears from the extender sequence. You keep everything you had up to that point, and then you have nothing at that point, but everything gets shifted up. So there's stuff above, but the optimist would say, well, I've made things look better because now I have agreement one more ordinal, right? And the miracle is that if you can keep iterating, then eventually things line up, right, by a kind of stationary set argument. Okay, so continuing the description, we also have limit stages, and at the limit stages, you take direct limits. Now, there was something omitted from my description at the successor steps, which is described here, which is when I said take the ultra power, you have to remember that, well, we're even in the situation where there isn't a measurable cardinal. So when I say take the ultra power, I can't necessarily take the ultra power of the model that the extender is coming from. If it's the top extender, then I can do that. But if it's one of the extenders in the model, then it only measures, it doesn't measure the whole model. And so what I do is I drop to the tallest initial segment of the model where that extender actually measures everything, and I take the ultra power of that. So this process of iterating has this additional step where the extender I'm choosing might not be total, so I go as high up in the model as possible where it is total, and then I take the ultra power of that. And okay, so iterability means that you don't drop more than finitely many times. And as long as you take, at each stage where you take ultra powers, you get a well-founded model. And at limits, when you take direct limits, you go to the last drop, you take the direct limit from there, you get a well-founded model. So iterability means everything is well-founded. I just noticed that I'm getting chats.
It was just a discussion about the audio quality.
Okay. So. Okay, so not too much more. So yes, so how do we know that this coiteration is well behaved? And that is again folded into the choice of X. So the choice of X has a lot of responsibilities. You might view this whole proof as by some complicated arguments shoving everything into iterability, and then the choice of X is guaranteeing many forms of iterability for you. Okay, so now rushing through analysis that I'm not going to explain fully, and that also a lot of it hinges on the actual definition of K going beyond the fact that K is an extender model. So the harder case hypothesis tells us that on the k side of this coiteration, meaning the iteration I, the unbarred side, the first thing that happens is you drop, right? So, oh yeah, I should say what I'm calling things. Yes. So the models on I are called M eta, and that's for eta less than or equal to theta. The extenders that I'm using on the iteration I are the F etas. Those are related to the models, to the extenders coming from the extender sequence of M eta. It's one of them. And sometimes M eta plus, so M eta plus 1 is the level of M eta that you drop to. So M eta plus 1 is an initial segment. N eta plus 1 is an initial segment of M eta. And it's a drop if they're not equal. So the indexing is a little funny. We have this eta plus 1 in the domain, the domain of I, of the iteration map. But that's an initial segment of the eth model. Okay, so saying that you drop at the first stage is saying that the N1, the first model you're taking the ultra power of, is actually a proper initial segment of M0, which is K. And then more analysis shows that this coiteration ends up with M theta, the last model of I, and M theta bar, the last model of I bar, lined up. Moreover, nothing happens on the bar side. So I bar is trivial. All of the extenders used on the bar side are actually just the empty extender, which means when you take the ultra power of the empty extender, implicit is that it's just the identity map. And the last model on the bar side is just K bar. So another way of saying this is that K bar is a proper initial segment of M theta. The reason it's a proper initial segment and not equal is because M theta is not sound. And I won't get into why, but it has to do with the fact that if you take the ultra power in this way of a sound structure, you get an unsound structure. And since K bar is sound and M theta bar is not sound, K bar is a proper initial segment. Okay, and then let's put mu zeta equal to the critical point of the extender you used, the extender you chose from M zeta. That's the critical point of the next iteration map. Let's let eta be the least stage of the iteration, of the coiteration, where M eta agrees with K bar below mu. So remember, we coiterated until all of K bar agreed, but I don't need to go that far. I'm just going to go out to the point where we've lined things up to mu. Let's let P be this M eta. Aha, so now I finally see what's analogous to the P from the proof from L, for L. This M eta is the least missing mouse in some sense, but we had to work harder to find it. Okay, so more analysis shows that eta is a limit ordinal, and there's some point along the way after which there are no drops in the interval from eta 0 to eta. And for every zeta in that interval, the critical point of the iteration map is mapped up to the preimage of nu, that's what we're calling mu, by the iteration map. Cx, and I'm labeling it because it all ties back into which x we took. Cx, the collection of mu zetas for zeta between zetas, this is not zeta 0, it's eta 0, in this tail of the iteration. All of the critical points in this tail of the iteration form a club in mu, and that club generates the top extender of P. So it generates a normal measure over P that's equivalent to the top extender of P. So I think I've already said the last sentence. And we're going to call this top measure, which corresponds to the top extender, UP. When I say top, I'm alluding to this structure back here. So I'm referring to the last interpretation of the last predicate as the top extender. So this P looks like that as well. This P looks like, has this top predicate. That's an extender, but it's equivalent to a measure over P. Okay, so this is all downstairs. Let's see. I'm worried about time. Gunter, should I draw a picture of this?
I think it's a good idea to draw a picture, and
yeah,
you don't have to worry about the time so much.
Okay, so let me change. So to draw a picture, I'm going to stop sharing that and then share my iPad. Is it visible?
Yeah, good.
Okay. So let's see. So first of all, we have new. Remember, that's rather large, and pi sends mu to nu. And then we have this delta here. This is the critical point of pi. And then we have k bar is some model of height. So maybe it's omega bar. Okay, and now so just a different picture. We're comparing k bar and k, and originally we said, oh, we have these two iterations. Okay, and the final models were okay, but then part of the analysis showed that I didn't give you, showed various things. So the first thing was that, well, I guess the first thing I said is that nothing happens on this side. So, and this is the identity. Okay, and another thing I told you is that there's a drop at the first step, so on the other side. So in fact, a better way to draw that would be so that we drop to N1, and then we iterate N1. Maybe a better way of drawing it. So there's no, there's no model there. And there might be other drops. Let me try one more time here. Sorry. So we have a drop, which I'll just draw as a kind of missing piece. And then we have some other iteration, and then maybe that goes on, and then we might have another drop. But eventually we have a tail where you don't drop. Okay, and this is equal, and this is an initial a proper initial segment. Okay, and then we looked at, we didn't need to go all the way to theta. We just looked at when things were lined up to mu. So let me change this slightly. Why isn't that? Yeah. So these are agree to mu, and then we kept going, sorry. There's more of this iteration, which just ends up, so this is eta, eta. This keeps going, nothing happens here. And then, whatever. So
there's a bar missing over the m theta on the bottom left.
Thanks. Okay. And then, so we just lined things up to, we just looked at when things were lined up to mu. Okay, now we're looking at this part of the iteration. And what I said in the last bit of analysis that is left out is you're going to mu, I'll leave myself some room. I'll draw horizontally this time. So when you're far enough out in between, zero, between some eta 0 and eta, what's going on is here's mu, and then you're just, and that's a limit. And so these critical points are being sent up to, here's mu zeta, and that's equal to I zeta eta of mu zeta. And they're forming this club, which I'm calling CX. And then CX, and then we have P, which is M eta. And then CX generates the top measure, the top extender, which is which codes a measure. Of P. Okay, and then the next step that I'm going to show you is, so this is all downstairs. So we found this mouse that was kind of the top, that was kind of missing from K. And then the plan is we're going to take the ultra power of P and that'll be well founded, we'll call it R. So we'll have pi tilde takes P to alt n p pi nu, which will be isomorphic to R when we take the Mistovsky collapse. So I think all of this is in the slides. Before I go back to the presentation, to the slides, should I explain anything in the iPad, on the iPad?
So when you say that CX generates the top extender, you mean by looking at all the things that eventually contain this sequence? Okay.
So by tails.
Mm-hmm.
You look at exactly what you just said.
Okay.
Okay, the same way, like this all traces back to Prickery and Cunin. And okay, so let's go back. To here. Okay. So that's where I left off. So now, so this R that I was just talking about is the lift up. I'm referring to that as the lift up, which is it's traditionally called. And again, the choice of X guarantees through not necessarily easily that R is well-founded and also iterable. And iterability, so if you take this R and co-iterate it with K, another co-iteration argument using similar analysis plus extra facts about K tells us that, well, actually the same facts ultimately that I left out, tells us that R is an initial segment of K strictly between nu and nu plus of K. So this top extender of R, which I'll call UR, it measures subsets of nu that belong to R, but R is strictly between, it's a level of K strictly between nu and nu plus of K. So R doesn't have all of the subsets of nu that belong to K. So we've made some progress. We've gotten, if you will, it looks sort of like a weak compactness measure over some new sized family of subsets of nu that belong to K, but it's not a measure, and we're looking for a measure. And moreover, it's generated by the image of this set of tails of the tail of the critical points downstairs. So you move those up by pi, you look at that club set, and that generates the top extender of R. Yeah, so that's great. We have a lot of understanding of what's going on, but we haven't gotten a measure over nu yet. We've only gotten a kind of a fragment of a measure. And we're going to need to put these all together for different x's in order to get the measure we want over nu in K. So for that, I want all of the notation to refer to x. So I had already started calling it x for C, but anyway, everything, all of the notation relevant to the argument that I outlined should now be decorated with x, so that we know where that it has to do, that it comes from, ultimately from the choice of x. And the idea for continuing the proof and for finishing the proof is to shrink the stationary family of so far good choices of x, so by a pressing down argument, to get to the point where if you choose an x and a y from the family, the smaller family, and x is contained in y, then you can understand how these critical sequences, or indiscernibles as they're often called, arising from x relate to the ones arising from y, and argue that the filter coming from x is extended by the filter coming from y. And then by choosing your x's, by choosing bigger and bigger x's and taking a union, we're going to end up with some filter u that measures everything in K, all the subsets of nu that belong to K, And then we still have another step because, sure, this U would witness that nu is a measurable cardinal in K, so long as we're able to show that U belongs to K. And so one more application of iterability, coiteration, etc., lets us argue that U belongs to K, and then finally we're done with the covering the Dodd-Jensen theorem. Of course, if we were, well, I'll say more about what we do for Mitchell-Steele indexing. And here in this argument, if you try to generalize this argument, well, sorry, if you just try to do this argument, you know, the way I've outlined, like I said, you need some analysis of how Cx and Cy compare, and we use the Jensen indexing at this step. So we didn't need it before, but it's just in this part that I'm suppressing, where the difference between the two indexing styles arises. We don't know how to make do with just the Mitchell-Steele indexing. I guess I can say that in the Mitchell-Steele case, we know that this is a club, but we don't know that it's a tail. And the difference between club and tail turns out to be some technical problem. If we assume some cardinal arithmetic, namely that if we're able to choose X so that it's actually closed under cofinality nu sequences, then this whole business about shrinking the stationary family one more time, actually a couple of more times, isn't necessary, because you can just argue, you know, there's a club set in X which generates an appropriate, you know, the lift up version of UX, and that club belongs to X, and then you can just use elementarity to get what you want. So there's a way around if you assume some cardinal arithmetic. Okay, so I think I'm wrapping it up here. So what has been suppressed? Obviously, I haven't told you what K is. The restriction to working below zero dagger avoids extenders that code more than just one normal measure. If you're working below a wooden cardinal, then comparison is not linear necessarily. And so we have to talk about iteration trees. The notion of iterability becomes much more complicated. Lifting up, the proof that Rx and Px are, that this lift up Rx is iterable is by some complicated induction on the cardinals of Kx, which already came up in the 95 paper. So wrapping it up, last slide, which I won't say in detail, is if you go one step further, right? We've generalized and generalized to K below a wooden cardinal. What about K with a wooden cardinal? When something goes wrong because of stationary tower forcing, namely you can change the cofinality. You can get a violation of this covering theorem if you have, you know, by forcing over K, if K has a wooden cardinal and something goes wrong. So the possibilities are maybe K doesn't think K, you know, V equals K. That's one possibility. Maybe the forcing extension doesn't realize that the ground model is K. And then the last possibility is that maybe K just doesn't have the covering property. So, but in any case, there's a sense in which this covering theorem cannot be extended further because of stationary tower forcing. And now I'm done.
All right, thank you so much. That was awesome.
I was worried that I wouldn't have a full hour of stuff to talk about.
No, we're really pretty lenient there when it comes to time. So
thanks for giving me the hour and a half.
well, thanks for giving us a longer talk. So yeah, so are there any questions?
Yes, I actually have a question. First of all, thank you for the wonderful talk.
Thanks.
So there are some covering theorems for more complicated models, right? For example, for the stack, the JSSS paper. So is there any hope to prove a stronger covering theorem like the one you showed us in this setting?
So there's hope that in any situation where you can work, right, there, as you know, there are versions of K that go beyond this anti-large cardinal assumption. And you would think that that the kinds of arguments in this proof would generalize. There are situations in which K exists but doesn't have a wooden cardinal, which are more generous than saying that there's no intermodel with a wooden cardinal. And you would expect that this result holds there, but I haven't gone as far as checking for whether that's actually true. I mean, I assume it is true, but I don't know. By the way, I can't see the full, let me stop sharing so I can see who's, hi.
Yeah,
Thanks.
Great.
Thank you.
Thank you.
Any other questions? Doesn't seem so. Well, okay, so then let me just thank you again. It was really a great talk. We
Thanks, Gunther.
thoroughly enjoyed it.
It's nice to see everyone, and I wish there was a possibility of having tea together.